All right, so welcome to Math 355 Abstract Algebra. I'm Professor Miller, and what I want to do today is talk a little bit about the course mechanics, always the most exciting part of the semester, and then talk a little bit about why are we taking the class. Now, to some extent, it's obvious if you want to be a math major, you have to take abstract algebra. Why is abstract algebra a required class? I was a postdoc at Brown for 4 years, and to be a math major, you had to do abstract algebra, but you did not have to do real analysis. They required you to do one of the two, and they chose abstract algebra. And again, anybody who wanted to go to math grad school went to both. This was a way to make the major more accessible, but it was abstract algebra that they chose to have required. And so what I want to do today, after we go through just the mechanics of the course, is talk a little bit about why would you care about something like this? I have degrees in math and physics, so my go-to is going to be physics motivation. I also do a lot of applied mathematics, a lot of mathematics of sports. And so at least 50% of the class here does sports to some level. And so I love drawing examples from stuff like that. But if there are things that you want to see, if there are things that interest you, I'm happy to try to find ways to work that into the class. So we're going to move at a decent pace. So class participation is 5%, homework 15%, midterm 40%. If there are multiple midterms, I will drop your lowest unless you tell me otherwise. And there actually was a situation where somebody did not want me to drop the lowest midterm. I will talk about that when this is not being recorded. Final exam, 40%. If you want, you can do a project for 10% of your grade. And if you want to do an even bigger project and have it count for even more, happy to do that. It's nice to have the ability of working with interested, motivated students, and we can personalize the class a little bit. So if there's something that you really want to explore, that's as valuable as doing some more standard problems if you understand the standard problems. Okay, so the prerequisites are Calc 3, although we're not going to use too much of Calculus 3, some basic combinatorics and basic set theory, and then some linear algebra. So we're not going to use too many of the results. It's more of the perspective of how do we prove things. So out of curiosity, have you taken real analysis yet? Okay, taking applied right now. Okay, so whichever you take first, real or abstract, is the harder one. And then the second one is the easier one because we are introducing you to proofs. And that's why I'm interested in exploring with you flipping this class so that we have more time to just do lots of problems, lots of proofs in class, and just really work on things. And so we have some interesting opportunities to do stuff like that. So if I'm in my office, it's office hours. My schedule is sometimes posted online. Unfortunately, I am dealing with some medical illnesses in my family, so my schedule is often in flux. Okay, so I want to start off by giving you some advice. You always want to be prepared. You never know when an opportunity is going to present itself. So, as I said, my name is Professor Stephen Miller. I went to grad school with somebody who was also named Steve Miller, who was born same year, same city as myself. He's 6 months younger, but much smarter. He skipped several grades, and he was graduating grad school the first year I arrived. It made a name for me because people said, wow, Peter Sinek is so great. He's actually looped other mathematicians, and he's on his second Steve Miller. So for mathematicians and academics in general, we love birthday conferences when we get old. That's what we really want. And so there was a birthday conference for my advisor. I was not on the organizing committee. There was already a Steve Miller on the organizing committee. You can't have two Steve Millers on the committee. But I was helping out with various things. And at the Institute for Advanced Studies, there was a dinner, and a couple of people had been asked ahead of time to say a few words about Peter Sinek. I was not one of the people asked, was not insulted. There were so many luminaries there. But I prepared a speech just in case. And after the set people spoke, they then took the microphone and went out to people in the audience and said, would you like to say a few words? And they handed me the microphone. And again, I think I've been a professor long enough, and he was such a great advisor to me. I think I could have done something off the cuff, but I was very glad that I had prepared ahead of time. What if the opportunity presents itself? What if I have to say something? And I had something prepared just in case, and it was valuable. So again, a lot of the time you're never going to use it, but if you can, try to be prepared. Related to this is if you have some slack in your schedule, read ahead. Things happen, life happens all of a sudden. You might have an extra meet, you might have a job interview, you might have a new opportunity, and you want to be able to allocate time for that. So if you can build a strategic reserve in your classes, try to do so. So your job is to be prepared for class. So that means reading the material or watching the video beforehand so that you have seen the material. This does not mean that if I don't make it, you can give the lecture. But if I'm giving a lecture on Stirling's formula, what do you think you should know before the lecture starts? Yeah, what the formula is, right? It doesn't mean you have to understand where Stirling's formula, where the proof comes from, but you should at least know what Stirling's formula is, maybe a little bit where it's used. And then ideally, if you don't understand the proof, where was the difficulty? There's a great math shirt where you have a lot of math scribbles, and then a miracle occurs, and then some more scribbles, and the other professor's pointing and saying, I think you need to be a little bit more explicit in this middle step. When you're looking at proofs, you want to try to get a sense of why is this true? It's very easy if somebody does a good job writing proofs to follow it line by line by line, but have no idea how did they ever think to do this? And so something that you can do multiple times becomes a technique. And one of the things I really want to emphasize in this class is how do we look at mathematics? How do we come up with proofs? How do we come up with ways of attacking problems? Right. So my job is to provide resources to help guide you through stuff like this, to be available. And then related to this is when there are opportunities to try to pass the opportunities on to you. Okay, so this was my advice. Here's the advice from my brother. He's reduced college to 3 points. Party less than the person next to you. Take advantage of office hours and mentoring. When you get to the real world or grad school, people are not as accessible as Williams. This is a wonderful, wonderful thing to be here. One of my favorite students was a math econ double major here, went to Harvard to get a PhD in economics, and he was at a charity auction, and one of the items you could bid on was an hour of office time from one of the professors. And it was the most bid on item in the auction. Here, we keep our doors open. Come see us, get to know us. Happy to go for a walk, grab a coffee, have a meal. And again, it's not just me, it's all the professors that are here. This is why you're at a school like Williams, is you want to get to know people, you want to get to know your classmates, you want to get to know your professors. You should get to know at least one professor well every semester. That way, when you need letters of recommendation, even if you're only successful half the time, you'll have 3 or 4 people by the time you graduate who can write a letter of recommendation for you, or who can connect you with people who might be able to provide opportunities. So one of my former students is studying in England right now, and he's decided he wants to take a year or 2 off from academia, and he wants to try out certain fields. Do I have any recommendations? Yeah. Here's a couple of Williams alums. Let me send some emails on your behalf. Within 2 minutes of sending out the emails, I've already got 2 people contacting him with opportunities. This is an incredible network here. This is the oldest alumni society in the country. Take advantage of this. As you're younger, you probably are not having too many interviews yet for jobs, but that will happen when you're older. If you ever want to do practice interviews or something like that, always happy to help you with something like that. I do not like emails, less than a day before something is due saying, I need to change when I'm handing this in. Can I have an extension? You should not do that. If you think something like that might happen, just reach out in advance. And this is a really good habit to get into. I might have a meet in 2 weeks. I don't know. It depends on how some other teams do and the seating comes out. Or I might have an opportunity for a wonderful summer internship. So you try to get your work done ahead of time so that you have the flexibility so if something like this comes up. But if you think something like this might be coming, then just let me know, in advance. And again, this is an undergraduate abstract algebra class. If you hand in a homework a little bit late, not a big deal. I will also drop whichever homework assignment helps your average the most. So all homework problems are worth 10 points. Some assignments will be worth more than other assignments. So everybody can have 1 week where just too much has come up and I just can't do it or don't want to do it. But as much as possible, you want to be planning ahead. So if you think something might be coming and you are not able to get the work done in time, just ask me for an extension ahead of time. And it's just a really good habit to get into. In the real world, you don't want to let your boss know, less than a day before a big presentation that you're not going to be ready. And I really want to get you ready for life after Williams. All right. So one of the big phrases you've probably heard in your life is a picture is worth 1,000 words. When we are trying to do proofs, we're going to talk about the notation we're going to use, the structure, how we're going to write things up. And after a while, you can just glance down and you can start to see relationships, connections. You really want to think about the notation you use. So everyone's done calculus. How would you write the derivative of the function f? So what is df dx? Good. How else could you write it? You could write it f prime. And both of these notations somehow involve the function f. So you can see it's something related to f. How would you write the antiderivative of f? Yeah. So you could do it with the integral sign. How else might you write the the antiderivative of f? I can be more specific. How would you write the antiderivative of the function little f? What do we often use to write the integral or the antiderivative of the function little f? We often use big F. So we often say, let big F be the antiderivative of little f. And the whole point of that is so that you can quickly glance down and see the relationship between these objects. And after a while, a lot of it becomes secondhand to just quickly look down. Now, sometimes notation that works really well in one setting does not work well in another. So when you take multivariable calculus, if I just write f prime, it's not clear what does that mean, because f is now a function of several variables. What am I taking the derivative with respect to? And then we start using partial derivatives. We start maybe using the gradient notation. And you really want to think what's going to go well. So I wanted to just show two pictures and just talk a little bit about what kind of information can you glean from this. So this is a picture that I used, you can probably guess, 2019. I'm going to guess it was close to the first day of class, fall 2019. And I am plotting the distribution of sunrise and sunset times in North Adams. That was the nearest major city to Williamstown that I was able to easily get data for. Does anything look surprising about the sunrise sunset times when you look at this? Yeah. Yeah, there's two jumps. So when you're looking at this, maybe it's slightly different, there's the change over here where it's going from decreasing to increasing. That's an interesting point as to what's happening then. But there's also two places where it jumps and it doesn't look continuous. Yeah, it's daylight savings, right? And that's why all of a sudden you have a boost in terms of what's going on. And so just by quickly looking at this, you can see two, maybe three places where something interesting is happening. That's what you want to do when you're looking at proofs. You want to try to find where's the interesting thing? Where is the real cleverness? Where's the key ideas versus just doing a bunch of little brute force algebra? And a lot of times when you have a difference, there's a real story. So the second example is a sports story. This is from a couple of years ago where the New England Patriots were playing the Los Angeles Rams in the Super Bowl. And if you look at a map of the country, or at least we'll say the continental 48 states, almost all of the country is either rooting for the Rams or rooting against the Patriots. So who is rooting for the Patriots and why? So if you look at this map, what do you see? New England, which makes sense. The New England Patriots should have the support of New England. Anybody else rooting for New England? Louisiana, any place else? Yeah, that little tiny thing. St. Louis. So you know why St. Louis and Louisiana were either rooting for the Patriots or against the Rams? It used to be the St. Louis Rams, and they moved to Los Angeles, and the people in St. Louis were pissed. The Rams had played the Saints, New Orleans Saints, in the NFC Conference Championship, and the referees missed a blatant pass interference on the Rams, which should have allowed the Saints to get a first down, run out the clock, and win the game. I have friends in New Orleans who actually work for the papers there. The headlines were brilliant. People were so pissed that they actually did not show the Super Bowl in many of the bars there. They actually rebroadcast an old Saints victory in the Super Bowl years before. There is a story as to what's going on. Sometimes the story is obvious. Okay, New England Patriots have supported New England. Got it, yeah. But these two other places, there's something big going on there. You want to try to look when you see things, where is something interesting happening and why? That's the big thing you want to try to get. Okay, so what I want to do now is I want to try to motivate the class through cryptography. So out of curiosity, how much have you seen of cryptography? Excellent. So I'm going to assume everybody has purchased something online. At least at some point in your life, you've made an online transaction. So what this means is you are telling a business, I want your product and I'm willing to give you money. And you have some secure way of transmitting your information to this business where they can verify it and they can charge your credit card. And you need to do this in such a way that your transaction is safe. So for cryptography, there's a lot of different ways of looking at what's going on. There's a lot of key components. Part of it is securities. I want to transmit things in such a way that only the intended recipient can determine what I'm saying. But that's not it. You also sometimes have to transmit information in such a way that the recipient can verify that it's coming from you. If you're a business and you get a request from somebody to buy 10 barbecue grills and charge this credit card, you really want to make sure that this is not a stolen credit card. And there's a lot of theft. And so how do you determine that this actually came from the claimed sender? And so what I want to do is I want to talk a little bit about basics of cryptography. So if you haven't seen anything before, that's fine. We're going to start in the beginning. And then after I do that, we will then shift to talking about the mathematics behind cryptography and how this is related to. Let me just pause for a quick second. Okay. So I want to start talking about some old cryptography. You're going all the way back to Roman times, to the Caesar cipher. Now, back then, it was almost enough to just write down your message so few people could read. But people might want a little bit more security than just writing something down. Now, for a lot of these, if I know how things are encrypted, it might actually be easy to decrypt it. And what we're going to see here is this is actually related to math that you've known since you were young, but you might not have realized that this is part of abstract algebra. So in mathematics, we sometimes like to use numbers rather than letters or objects because we can add numbers to each other. If I have 3 apples and 2 oranges, I just have a lot of fruit. But if I have, +1 and I have, 2 negative ones, I can add all that. So whenever possible, it's nice to have things being mathematical. So rather than using letters, I could use numbers. And I can either go from 1 to 26 or from 0 to 25 if I want to do the letters of the alphabet. Do I want to start counting at 0 or at 1? And there's good reasons for both. And so my first question is, I want a function that's going to map the alphabet to the alphabet in such a way that different letters go to different letters and all letters are hit. So maybe A goes to Q, B goes to Z, C goes to C, D goes to F, and et cetera, et cetera, et cetera. That would be one choice. And then maybe another choice is A goes to A, B goes to Z, C goes to Q, and that would be another choice. And I would have lots of different choices, right? Does anybody know how many choices I would have? So how many choices do I have for what A goes to? 26. And how many, once I choose A, how many choices are there for B? 25. So it's 26 factorial. I'll let you do that later tonight and see just how large that is. Do I need both conditions? Do I need to say each different letters go to different letters and every letter is hit? So a bijection would mean that the function is 1-to-1. So 2 different inputs can't go to the same output. And it's onto. That means everything gets hit. And so do I need both of these conditions, or does one condition imply the other? If I know different letters go to different letters, does that mean every letter is hit? So imagine we had a letter that wasn't hit. Give me a letter H, okay? H is not hit. So we have 26 letters of the alphabet, and I need a map such that different letters go to different letters, but H is never hit. Is it possible for the 26 letters to go to the 25 remaining letters such that different letters go to different letters? No. We have, this is the pigeonhole principle or the box principle, that if you have, n plus 1 pigeons and n boxes, and we carefully, because we don't want to hurt the pigeons, we carefully place each of the n plus 1 pigeons in a box, at least one box has to get 2 pigeons. If there are 10 pigeons and 9 boxes, if each box has at most 1, that can only account for 9 pigeons, 1 pigeon is left over. So over here, if different letters go to different letters, then that immediately gives me all letters are hit. Conversely, if all letters are hit, then different letters have to go to different letters. So sometimes we like to see what is the weakest set of conditions we need for something. So when we get to the definition of what is a group, we're not going to necessarily give the weakest definition, but we'll give a good definition. And you can always ask, can I weaken this? What is the most basic fundamental thing we need? Now, lurking in the background here, this is extremely important, is that we have a finite set. We only have a finite alphabet. Any Dr. Seuss fans? No. He wrote a book once called On Beyond Z, where the standard alphabet was not enough, and so he added more letters. But even there, it's still only a finite number of letters. There is a huge difference in mathematics between the finite and the infinite. Once you get to the infinite, things are very difficult, and you have to be extremely careful. And so over here, we were able to say, look, if there are 26 letters and one of them isn't hit, I've got 26 letters going into 25 boxes. At least one box has to be hit twice, so I can't have different letters going to different letters. If I had infinitely many letters, it would be different. So imagine I have infinitely many letters. My letters are now going to be 0, 1, 2, 3, 4, 5, going all the way up to infinity. Then I can send different letters to different letters by just sending send 0 to 1, 1 to 2, 2 to 3, just shift everything by 1. And so if we do that all of a sudden, these two conditions are not the same. We're not going to be working with infinite alphabets now, but we will later. And it's just something to be aware of. Okay. So we talked about how we don't need both conditions. So just for some notation, let's let x be the input letter, and then f of x will be the encrypted letter. What's the simplest function you can think of for f? It may not be a good choice if you want security. What's the simplest function you can think of? Yeah, f of x is x. I just don't encrypt. This will not be that hard to decipher. Now, there is another simple choice. I could take f of x equals c. No matter what input you give me, I just give you a fixed output. The problem is this would be stupid. Then whatever message you give me would just become c, 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 c. And there's no way we could say what's going on. So if I take the constant function, this is going to be terrible for encryption. So the next simplest function is to combine the two, is combine the identity function with the constant function. And let's look at f of x as x plus c. And we're going to have to figure out, how do we want to interpret x plus c? And so, for example, the standard way we do it is, let's say c equals 3. What this means is shift every letter down by 3. So if we shift a by 3, we would get d. If we shift b by 3, we would get e, and so on and so on and so on. And things become a little bit complicated at the end. So if we shift w by 3, we get z. But what would happen if you shift y? Shift y by once you get to z. I'm sorry, x. We shift x by once we get y, twice we get z, 3 times. What should come out to z? Yeah, it makes sense to say a. So it is 9 o'clock now. What time will it be in 5 hours? 2. So you are telling me that 9 plus 5 equals 2, and we're in the 300 level class at Williams. Does 9 plus 5 equal 2? Does 9 plus 5 equal 2 on a clock? Can we tell the difference between 14 and 2 on a clock with 12 hours? We just wrap around, they're the same. And so this leads to the concept of equivalence, which is going to be a big theme in the class. For a lot of things, we don't care if they're identical. We just care if they are the same for certain key properties. And so on the clock, all we care about is, do you differ by a multiple of 12? If you differ by a multiple of 12, we're going to represent you with the same number on the clock. Well, rather than doing this on a clock, we could do this with the alphabet. And we'll say that the letter following Z is A. We're just going to wrap around. So how many hours would the alphabet clock have? 26. And so we'll see later that clocks are really good in group theory when they either have a prime number of hours or the product of two distinct primes. Those are going to be extremely valuable. So if I give you the encryption is I shift every letter forward by 3, how would you decrypt a message? Yeah, just go back by 3, right? It's not going to be that hard to decrypt. What if I don't tell you how much you shift by? Okay, but is it something that you could do? So how long would it take you if I didn't tell you what I'm shifting by? How many possibilities would there be to try? 26. Assuming I'm not an idiot, how many would there be to try? 25, right? We'll assume I'm not going to give you the don't do anything. I'm not going to give you C equals 0. So there's only 25 or 26. So as long as I know the method you're using, even if I don't know the details of how you're doing it, it's not so bad. All right, what if I try to make your life difficult? And what I'm going to do is I'm going to choose 100 different shifts. And I'm going to first shift by C1, and I'm going to get an encrypted message. Then I'm going to shift by C2, then by C3, then by C4. I'm going to do this 100 times. There's 26 choices for each. We're talking about 26 to the 100. So how many possibilities would there be if I give you 26 to the 100? That's huge. So could you decrypt this in a reasonable amount of time? So it looks like the Caesar cipher is not that secure if I only do it once. But if I do it 100 times, does it seem secure? 26 to the 100 is huge. There are less than 10 to the 100 subatomic doohickey whatchamacallit thingamajigs in the universe. So if you had a universe of universes, that gets you up to maybe 10 to the 180. 26 to that is huge. But is it really that bad? If I shift something by 3 and then I shift it by 2, what's that the same as? So if I shift something by C1 and then by C2, it's the same as shifting by C1 plus C2. So if I do 100 shifts, yes, there are 26 to the 100 possibilities. But at the end of the day, if I do 100 shifts, it's the equivalent of just doing one shift. And so how many possibilities are there? 26. It's not secure at all. It seems like it's a lot more secure. And so a lot of times people have crypto systems which they think are secure. And then somebody points out a very clever attack. And so it's often extremely difficult to show that someone can't do something. We're going to later see cryptography based on primes. And the hope is that these systems will be secure, but one never knows. Okay, so decrypting this is not that bad. If I try to do the trick of doing 100 consecutive shifts, it seems bad at first, but it's really not so bad. And the idea is a shift followed by a shift followed by a shift is just a shift. So there's a lot of ways of writing this. So this is the linear way of writing it. Underneath A, I write D, underneath B, I write E, and so on and so on and so on, just going all the way down. And this shows you how the Caesar cipher works. And if you give me the letter E, I shift it down to H. If you want to decode H, you shift it back to E. Another way you could write this is you could write it as a wheel. I actually prefer to write it as a wheel, even though the tech code is a little bit more challenging to do it this way. This emphasizes the cyclic nature. And we just keep wrapping around and around and around. And in this way, we can see Z goes to A. There's nothing special about the beginning or the end of the alphabet. When I write it linearly, it seems like there's something special just because of how things are presented. And so, if I wanted to just do something, if I gave you the phrase meet at 10, I'll convert all the letters to the numbers. So I'm going to start counting with A as 0. So M, which is the 13th letter of the alphabet, would become a 12. I add 3, and I get, and so that would be the message. And then to decrypt, I would just subtract 3. And when I do my adding and my subtracting, I always have to be careful. If I go over 26, I then have to subtract off 26 to just bring me back to have a number between 0 and 25. And so it's not that bad to encrypt or decrypt using something like this. And we saw trying to do multiple Caesar ciphers is not going to lead to something that's more secure. So we have to ask, is there a better way to do the encryption? So we could try a more complicated function. So rather than doing f of x as x plus c, let's do maybe f of x as ax plus b. And again, rather than running, let's first walk. Let's try to do a simpler case, build up some intuition, and then work. So rather than working with a 26-letter alphabet, let's work with a 6-letter alphabet, A, B, C, D, E, F. So how many hours are on my clock now? 6. Whenever you have something that's complicated, it's always good to try to break it up into simpler pieces. I would much rather do a lot of easy problems than one hard problem. So let's break things up into easy problems. So there's 2 things going on. I take x and I multiply by a, and then I take that and I shift it by b. I understand shifting by b. Shifting by b is very simple. Any choice of b is going to work. So how many choices for b are there? There's going to be 6 choices for b, because I'm on a clock with 6 hours. I can shift by 0, 1, 2, 3, 4, or 5. And now we have to start to think about which A's will work. So what are the possible A's that could work? So we're doing a 6-hour clock. So what are my choices for A? It's okay if they don't work. Just give me the candidate set and then we'll see if they work. So what are the candidates? 1, what else? 2. So give me them explicitly. 1, 2. Yep. 3. Anything else? 6. Now, if I shift by 6, if I multiply by 6, I'm basically sending everything to 0. So we know that if we take A equals 6, that's not going to work. If we take A equals 1, that's just the identity, that's going to work. So it's the 2, 3, 4, 5 that are more interesting. And so let's try to figure out what's going on. So I'm going to take b equals 0 and just look at f of x equals ax. Because if I can figure out what a work, I can easily tack on the b. I'm breaking this into a simpler problem. And so, let's say, so if b, let's not do that. Let's do it this way. So if I take a equals 1, I can look at what do I get for the different values 1, 2, 3, 4, 5, 6 when I multiply by 1. I just get back the set 1, 2, 3, 4, 5, 6 again. If I take a equals 2, 1 goes to 2, 2 goes to 4, 3 goes to 6. Why does 4 go to 2 when I multiply by 2? It's mod 6. It's on a clock with 6 hours. 4 times 2 is 8. And when I reduce it by 6, because I have a clock with 6 hours, I get 2. 5 times 2 is 10. So when I subtract 6 to get it down, it's just 4. And then 6 times 2 is just going to be 6 on the clock. When I do 3, I would get 3, 6, 3, 6, 3, 6. When I get 5, I get 5, 4, 3, 2, 1, 6. So we see 1 works, 2 fails, 3 fails, 5 works. And I claim 4 and 6 also fail, and I don't even have to do anything new. And the reason is I know A equals 2 fails. I have to have different letters going to different letters, or I have to have every letter hit. If I take A equals 2, I don't have different letters going to different letters, right? Both 1 and 4 go to 2. 2 and 5 go to 4. 3 and 6 go to 6. Different letters are not going to different letters. Or I can say, I don't hit all the letters. I only get 2, 4, 6. If I have an encrypted message and I have a 4, is that 4 coming from a 2? Or is that 4 coming from a 5? I don't know. And there's no way to know. Now, I claim that I don't have to bother calculating A equals 4 or 6. And the reason is 4 is just 2 times 2. I know multiplying by 2 fails. So if I multiply by 2 again, it doesn't matter. I've already failed. I'm not going to get more distinct numbers. I might even get less. Similarly, 6 is 2 times 3. So once I multiply by 2, if I multiply by 3 again, I know I can't get more distinct numbers. In fact, if I multiply by 6, everything just goes to 6 on the clock. So if you look at this, we have a very small amount of data. We have 1 and 5 work, 2, 3, 4, and 6 fail. So can anyone tell me what 1 and 5 have in common when we look at things on a clock with 6 hours? 2 and 3 are factors of 6. So do you know a nice, concise way of saying this? Relatively prime. So 1 and 5 are relatively prime to 6. 2, 3, 4, 6 are not relatively prime to 6. So it seems like maybe if we choose A to be relatively prime, that's going to work. Now you have to be extremely careful when you do stuff like this. Here's one of my favorite problems. It's just taking a while to write. All right. Can somebody tell me what 16 over 64 is in lowest terms? 1/4, good. 19 over 95? 1/5. 49 over 98, I'll give you a harder one. 1/2. Let's do one more. 12 over 24. I'm sorry? I get 1/4. Do you want me to show you my algebra? 16 over 64, I cancel the 6's and it's 1/4. 19 over 95, I cancel the 9's, it's 1/5. 49 over 98, I cancel the 9's, it's 4/8. So clearly, 12 over 24 is I cancel the 2's and I get 1/4. Just because something works for a while doesn't mean it's going to continue to work. But the more times it works, the more confident you are. But you've got to be careful. Maybe you're checking a very special set. And not surprisingly, this is an extremely special set, which numbers work. Sometimes what you do in a problem like this is I would not display the 49 over 98. I would keep that in reserve. So if somebody does, let's choose another one at random. Let's do, I don't know, let's do something hard. Let's do 49 98s. And so just because something works for a while does not mean it's going to continue to work. So we looked over here with when we had 6 hours on the clock. We could do another clock. We could do a clock with 8 hours, with 11 hours, with 15 hours, with 12 hours. And if we kept doing this again and again and again, we would see every time we do this, the only A's that work are the A's that are relatively prime. Okay. If the only ones that work are the A's that are relatively prime, now we're beginning to feel that maybe something is going on here. It's not a proof yet. And a lot of this is going to be stuff that we'll see later in the semester. Okay, so we found the pattern. So for the 26-letter alphabet, how many numbers do you think are relatively prime to 26? Or which numbers do you think are not relatively prime immediately? 2, what else? 13, 26. So which numbers do you know are going to have a common factor with 26? All the evens. So we lose all the evens. That's half the numbers. We've lost 13 numbers. Now we have the odds. Which odds do we lose? Which odds have something in common with 26? Just 13. So we would conjecture that there would be 12 choices that would work. All the odds other than 13. And if you go through, it turns out it works for all of these. And so now we have, for this is called the affine cycle. We have 12 choices for A. We have 26 choices for the shift B. So we have 312 choices. Now, one of these choices will be choosing A equals 1 and B equals 0, which does nothing. Okay, so if you want to eliminate that, there's 311 choices. This is a lot better than the 25 choices for the Caesar cipher. This would not be pleasant, but if I told you your entire grade for the semester would be to decrypt a message. Yeah, 312, not a problem. Yeah, I can do 312. So this is not enough to be secure. There are things you can do to try to make it better. And I'm not going to go into that now. If people are interested, we can definitely talk about stuff like that later in the semester. But we're beginning to see, as we look at more interesting functions, we have more possibilities. It's getting harder to decrypt. And it's getting a little bit harder to show what can be done. It was a little bit of work to show which A's are doable. Okay, so this is a chance to introduce some notation that we're going to see later in the semester. And that's one of the reasons why I like doing this on day one, is we get to meet some of the key functions. So this is the Euler-Toscan function, which is often denoted by phi. And so we'll define phi of n to be the number of numbers from 1 to n that are relatively prime to n. So this means that they don't have any factor in common with n other than 1. And the reason is 1 divides every number. So you always want to think, why am I choosing this as my definition? Well, since everything is divisible by 1, if you consider two numbers that share 1 to have a common factor, then every number has a common factor with every other number. And this notion of common factor and relatively prime would be stupid, because no numbers would be relatively prime. So we define numbers to be relatively prime if the only factor they share is 1. So let's try to figure out how many numbers are relatively prime to p if p is a prime. So imagine I give you p equals 5. Which numbers are relatively prime to 5? 2, 3, 4, anything else? So the only factor you can have in common with 5 is 1. So it's not just 2, 3, 4, something else works. Nope, it's not 5. What else has a common factor, has no common factors with 5 other than 1? There's 2, there's 3, and 1. 1, 2, 3, 4. So if I give you 5, then phi of 5 would be 4. What if I give you the number 7? How many numbers from 1 to 7 are relatively prime to 7? 6. 1, 2, 3, 4, 5, 6. So in general, if I give you a prime, how many numbers are relatively prime from 1 to p to p? P minus 1. So we have a really nice formula for phi of p. Phi of p is going to be p minus 1. And so I love the idea of baby steps. Prove something simple and then make it a little bit more complicated. So now that we understand how many numbers are relatively prime when we have a prime input, where do we go from there? Well, there's two possibilities. I could look at the product of two distinct primes, or I could take the square of a prime. So let's imagine now I have p squared. So if you want for the definiteness, let's say we have 25. So I'll go to your screen. So we have, p squared is going to be 5 squared. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, ... 24, 25. Which numbers are going to have a common factor with 25? Five. What's the next one? And what's the next one? So it's going to be 5, 10, 15, 20, 25. So if you think about this, we had p squared numbers, and how many did we throw away? We threw away 5. So we throw away p numbers. So it'd be p squared minus p. Another way of looking at it is we throw away p. What's the next number we would throw away after p? 2p. And then 3p, p minus 1p, and then p squared p. Or p squared, which is just p times p. So this would be a proof that if I look at how many numbers are relatively prime to p squared, it's p squared minus p. What about p cubed? Which numbers do you think I would lose if I gave you p cubed? So what's the first one we would lose? The first one we would lose would be p. What's the next one? 2p, 3p, and we'd go all the way up to p cubed, so I can write that as p squared times p. So if I'm giving you p cubed, I would lose p squared numbers. And so if I want to figure out how many numbers are relatively prime to p cubed, it would be p cubed minus p squared. And then a nice problem would be, see if you can figure out what is the pattern in general. If I gave you p to the 4th, p to the 5th, p to the 6th, can you come up with a general formula? The next thing to look at is, what if I give you a product of 2 distinct primes? What if I give you 2 different numbers p and q? Well, we can try to build some intuition. So let's say I give you p equals 2, q equals 3. So I have 1, 2, 3, 4, 5, 6. And we've already seen that the numbers that we lose 2, we lose 3, we lose 4, we lose 5. So phi of 6 would equal 2. What if I give you p equals 3, q equals 5? So now we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Which numbers do I lose now? So which numbers from 1 to 15 share a factor with 15? So I lose 3, I lose 5, I lose 6, 9, 12. Sorry. We lose 10. So when you're doing something like this, you want to make sure you do it in such a way that you don't miss anything. So another way to do the calculation is, let me get rid of all the multiples of 3 first. So I get rid of 3, 6, 9, 12, 15. Now let me get rid of the multiples of 5. So I get 5, 10, and I would get rid of 15 again. So now I would get phi of 15 equals 8. Let me just record something. So phi of 2 equals 1. Phi of 3 equals 2. Phi of 5 equals 4. We got these because we know what phi is for prime input. Can you see how to get, phi of 15 is 8 from phi of 2, phi of 3, phi of 5? Yes? 2 times 4. So maybe phi of 15 is phi of 3 times phi of 5. What about phi of 6? Well, that is actually phi of 2 times phi of 3. So maybe if I have a product, the number of numbers relatively prime to the product is the product of the numbers that are relatively prime. So in other words, phi of a product is the product of the phis. It turns out that this is not true in general. It's only true if your terms in your product are relatively prime. You can see that this has to be true because let's say we did P equals Q equals 2. So how many numbers are relatively prime to 4? Which numbers do I get rid of? 2, anything else? So we would get phi of 4 is 2, but phi of 2 times phi of 2 is just 1 times 1, which is not phi of 4. So a lot of times you can disprove a conjecture by just doing a specific example. And so before I spend a lot of time trying to prove a theorem, let me look at some special cases. Oh, okay, I can immediately see phi of a product is not always the product of the phis just by looking at 4. So the formula worked sometimes. We all laughed, hopefully, when we looked at 16 over 64. It held 3 times, but did not hold when we got to 12 over 24. All the time, you can find relationships that work for a while, but then stop working. Because we've got to be very careful. Now, in this case, it turns out we can prove that if P and Q are distinct primes, then phi of PQ is equal to the product of the phis. And the proof is not too bad. And so first we say, well, what numbers do we lose because they're multiples of P? We lose P, 2P, 3P, 4P, all the way up to Q times P. So how many numbers have we lost in this first row? How many multiples of P are there? Q, right? We have 1 times P, 2 times P, 3 times P, all the way up to Q times P. Now we look at the multiples of Q. How many multiples of Q are there? We have Q, 2Q, 3Q. I'm not going to risk saying the next one because of my accent. That would not go well. So I'll go all the way down to P times Q. How many multiples of Q are there? So how many multiples of Q do we have? P. So I had PQ numbers. I lost Q because they were multiples of P. I lost P because they were multiples of Q. But there was one number that was a multiple of both P and Q, the number PQ. I threw it away twice. So I have to add it back once. And so now, because I believe the answer might be P minus 1 times Q minus 1, phi of P times phi of Q, I actually just check and see if I expand this out, do I get PQ minus Q minus P plus 1? Yes, I do. And this is where knowing the answer helps in terms of trying to figure out how can I simplify the algebra. So we proved that if the two terms in the product are distinct primes, then phi of a product is the product of the phis. This does not hold in general, but for a lot of applications, this is all we need. Let's see. Class ends at, is it 8:40, 8:55? Or it's been so long since I've taught a Tuesday, Thursday class. 8:45, okay. So we've still got about 15 minutes. So well, let me quickly do why primes. So let's try to motivate why we use primes in encryption. Now, a lot of this is in flux now because quantum computers can break very quickly codes based on primes, which means e-commerce, because you're both interested in economics, is going to have to shift and has already started to shift away from encryption based on primes to new methods that would be more secure when the quantum computers become durable. Right now, I know for a while the largest number the quantum computers could factor was 21. They might have hit 35. They're not at big numbers yet, but at some point they will begin to factor larger and larger numbers. So I'm going to show you two different schemes for encryption. In the first, I take P and Q to be 200-digit primes. These are huge numbers. I'm going to multiply them together, and I'm going to call that N, and I'm going to make N publicly available. And the password is either P or Q. So there's two possible passwords, and each of them have 200 digits. That's method one. Method two is I'm going to choose a 5,000-digit number at random. And to get in, you have to give me that correct 5,000-digit random number. So which do you think is harder? To guess a 5,000 random digit number, or I tell you N, and you just have to give me one of the two factors, and N is a product of 200-digit primes. Which do you think is going to be easier? Which do you think is going to be harder? Yeah, because you have to get 5,000 things correct. I could forget if I wanted to that P and Q have to be primes. Let me just try all 200-digit numbers and see what divides N. There's far less things to try than the 5,000. So it seems like the 5,000 digit is the more secure approach. But remember, we already saw earlier today when we did 100 straight Caesar ciphers that wasn't any more secure than doing just one. So unfortunately, sometimes things that seem secure are not. It turns out that the more secure system is actually the first. And the best way to explain it is the phrase, I'll know it when I hear it. So in the first case, imagine you have a computer. The computer does not need to know the password. All the computer needs to do is know the number N and know how to divide. If you capture the computer, you cannot torture the computer and try to figure out what the password is. For the second one, the computer needs to have the password stored somewhere internally. And then when you give a 5,000-digit string, it has to check your string with what it has. This opens up the possibility of torturing the computer. And so the second system, while it's much harder to get 5,000 digits than 200, is actually far less secure because the computer has to know the answer. And there are things you can do. To just put some things in perspective, I told you earlier that there's around 10 to the 80 subatomic things in the universe. Imagine every atom in the universe was a universe, and every atom in that universe of universes was a supercomputer capable of checking 10 to the 15 items a second. That's better than what our supercomputers can do. Let's round up. There's about 3.2 times 10 to the 7 seconds in a year. And so we could check about 3 times 10 to the 182 per year. The universe is about 15 billion years old. So in the life of the universe, we'd be able to check about 5 times 10 to the 192 numbers. We need 200-digit numbers. We need something of size 10 to the 200. This is telling you that if you want to do a brute force check, a universe of universes where every atom is a universe and every atom in that universe is a supercomputer running since the dawn of time, that's not even enough to make a dent in the problem. That gives you some idea of how secure it is, and that people felt that stuff like this would be safe for quite a while. With some knowledge from mathematics, we'll see that stuff like this is not nearly as secure as you would think. The calculations are not quite as bad. And so what I want to do for the very last few minutes is just briefly introduce some of the key ideas we're going to be seeing for the rest of the semester. So this is called the RSA algorithm due to the mathematicians Rivest, Shamir, and Aldwin, who came up with this. There are other people who came up with it potentially earlier, but because things were classified, it's always sometimes a challenge of giving credit to who was the first one to discover something. Right? So let's say Alice is trying to communicate to Bob, and Charlie or Eve is always trying to eavesdrop. In the subject, you always use these names. It's always Alice talking to Bob. Charlie or Eve is always the eavesdropper. You want things that are easy. A, B, first two letters of the alphabet. People sometimes use Eve for eavesdropper, with really bad language skills. So Bob is going to do the following. I could put your subscripts B on all of this to say that these are coming from Bob. Bob chooses a secret P. Some prime, let's say 15,217, chooses another secret prime Q, say 17,569, and chooses a number D, 809,98505. And then Bob is going to make public the product of those two primes, and he's going to make public a special number E. And right now we should have no idea where these are coming from. But these numbers are going to have some interesting properties. It turns out if I multiply E and D, and I imagine that I'm on a clock with P minus 1 times Q minus 1 hours, which is phi of PQ, then the remainder is 1. So somehow Bob has found two numbers that multiply to 1 plus a multiple of the number of hours on our clock. And here's what Bob does, or what Alice does to send a message to Bob. She takes her message, which is going to be something less than n. And if a message is bigger than n, you just break it up into smaller blocks and you send each block one at a time. And so Alice takes her message and she raises it to the nth power and looks at the remainder on a clock with n hours, P times Q hours. Now in practice, E could be a 200-digit prime number. So we would have to think about how can we quickly calculate something to the 10 to the 200th power. And so this is something that we're going to have to deal with later in the semester. So this is the difference between pure mathematics and applied mathematics. In pure mathematics, you could say, do the calculation. In applied mathematics, the question is, okay, yes, but I want this to be done before the universe dies a heat death. I can't afford to wait 15 billion years for the calculation to finish. So how can we do this in a reasonable amount of time so that we can actually complete our online transaction? When you're purchasing something online, you don't want to wait 3 hours for things to be verified. So we somehow have to find a way to compute this in a reasonable amount of time. Do you all agree that in principle, this isn't that bad? Just keep multiplying m by m and keep reducing it every time you multiply. It's just, we don't have time to do it, but in principle, this is not intrinsically hard. It's just potentially hard to do quickly. And the key insight was finding a way to do this quickly. And then we get this new number, x121209473. And Alice then sends this number to Bob. And Bob takes that number and he raises that number to the dth power. And remember, E and D are these very special numbers chosen so that x to the d, when you do the math and you look at its remainder on a clock with n hours, is 195632041, which is the original message Alice sent. So this is amazing. Alice is able to take a message, send it to Bob, and Bob is able to decrypt it. Now, what do we need to decrypt it? We need this number D. So the question is, and this is what's responsible for the security of the algorithm, is there any way that Charlie or Eve can figure out D from what's publicly available? So we don't know the primes P and Q, we know N. Well, if we knew N and we had a great way to factor, well, if I knew how to factor quickly, I could then find P and Q. If I know P and Q, I can then find P minus 1 and Q minus 1. And it turns out if I know P minus 1 and Q minus 1 and I know E, I can then figure out D very easily. There's a very simple way to do that. This is called the Euclidean algorithm. Right now, we do not know a fast way to factor a number. In principle, factoring is trivial. Take your number, divide by 2. divide by 3, divide by 4, divide by 5, divide by 6, divide by 7. Do I really have to divide by 4 after I try dividing by 2? No. I could make things more efficient, but I'm just trying to show you that in principle, factoring is easy. Just keep trying all the numbers, and eventually you'll get either something divides it, or if nothing divides it, it's prime. So in principle, I can factor a number, but we don't know any fast way to factor a number. Amazingly, we do know a fast way to determine if a number is prime without knowing its factorization. This is strange. It blew my mind when I first saw this. I can actually tell you if certain numbers are composite without giving you a factor. Now, of course, one way to tell you a number is composite is to give you a factor. But it turns out that composite numbers have different properties than primes, and there are some simple tests you can do that can often detect whether or not you have a composite number. It doesn't work for every composite number. There's a lot of really interesting math going on. So one of the things we're going to learn in the class is how do we do all of this quickly? The other thing is, imagine that Bob received one digit in error. And so instead of getting 7-3 at the end, Bob gets 8-3 at the end. When Bob decrypts, instead of getting the correct message, Bob gets something very, very different. So one of the questions you always want to ask is, how stable is your system? Can you survive if there's a small mistake? And when you're doing transactions, you want to be very careful. Have you ever bought something at the supermarket? What do they do when you buy it? They scan it. And so there's a little barcode. And they have some tests to make sure that it scans correctly. Now, it's possible that it could have scanned incorrectly but passed all the tests. But they do some very simple tests so that if you're buying detergent, it's not going to come up 10 cents or $1,000. It's going to be something reasonable. They're going to hopefully identify this as detergent. What if it doesn't scan correctly? What do? So they try to scan it, it doesn't work. What do? Scan it again. Exactly, they scan it again. And what if it doesn't work when they scan it the second time? Excellent, then they look at it. So what you do is you have an algorithm that's easy to do. Scan. Damn it, it's not working. Now let me do the hard algorithm and look it up. This is a great idea in mathematics. You often have different algorithms. You do the simple, easy one as long as possible. And then if that breaks down, then you go to the better algorithm, which may be slower, but you know it's going to work. And so we're really going to be concerned on efficiency. We're going to be concerned, what happens if there's a small error? Can we design our system in such a way that we can survive? If I did something with the Caesar cipher and I got one letter wrong, you could still figure out most of the message, right? And if there's one letter wrong, you can easily figure out what's going on. Here, one mistake completely changes everything. And so there's a lot of implementation issues. So one of the issues is, how do we find large primes? How large is large enough for a given level of security? Depending on the problem you're doing, different levels of security are needed. How do we find an E and a D such that E times D is 1 mod a clock with P minus 1 Q minus 1 hours? How do we calculate M to the E mod N efficiently? You have E's of size 10 to the 200. I can't do that many multiplications. Supercomputers can't do that many multiplications. We have to find a better way of doing this. And then the last one, which is completely open, is there any way that Eve can determine D from the publicly available E and N? Right now, we do not know. If you know a way to do that, do not tell me when things are being recorded. Okay? We will figure something out. Okay? So right now, a lot of things are really exciting in terms of where things will be in another 10, 20 years. And already people have started to shift from cryptography based on primes to other systems that they believe will be secure against the quantum computers. Because what can go on right now is nefarious powers or businesses can be recording information. They may not be able to decrypt it now, but they can decrypt it potentially in a few years. And so already people have started to shift. All right, so this is a good place to stop for today. Stop the recording.